Chi-square test. The chi-square test is a statistical method used to analyze categorical data. Its primary purpose is to determine whether there is a significant association between two categorical variables or whether an observed distribution differs from an expected one. There are two main types: the chi-square test of independence, which checks if two variables are related, and the chi-square goodness of fit test, which assesses whether observed frequencies match expected frequencies. This test is commonly used when the data consists of counts, or frequencies, not averages or percentages. Welcome, everyone! In today's session, we're going to focus on practical techniques using the chi-square test, particularly relevant when working with discrete or categorical data. Here's what we'll cover. First, we'll look at the one-variable chi-square test. This is used when you're comparing a single categorical variable to an expected distribution, also known as a goodness of fit test. Next, you'll notice the two-way table item is crossed out. This means we're not covering it in today's session. You may find it in advanced materials, but it's out of scope for today. Finally, we'll explore cross-tabulation, which helps us understand the association between two categorical variables. By the end of the session, you'll have gained solid understanding of when and how to use these methods in real-world problem-solving. In this slide, we're looking at the three primary applications of the chi-square test, depending on the nature of your variables. Let's break them down. 1. One-variable test. Goodness of fit. This is used when your y is numeric, typically a count of occurrences, and x is categorical. For instance, you might want to see if the number of defects is equally distributed across different product categories. 2. Two-way table. This version is applied when both your x and y are numeric counts, but we're comparing them across two dimensions. It's often used to see if distributions differ by group. However, we are not focusing on this version in this particular session. 3. Cross-tabulation. This is the most common chi-square test application where both x and y are categorical. We use it to test whether there is an association or independence between the two variables. For example, does customer satisfaction rating differ by region? The gear icons visually represent the connection between these methods. They're all part of the broader chi-square toolkit that helps us make sense of categorical data relationships. Let's understand what the chi-square test really is. The chi-square test is a non-parametric statistical method used when you're dealing with categorical data, meaning data that falls into distinct groups like regions, product categories, or yes/no answers. This test helps answer two critical questions. 1. Are the observed frequencies different from the expected ones? For instance, if we expect 50% of survey responses to say yes, but only 30% do, the chi-square test helps us measure whether this difference is statistically significant. 2. Are two categorical variables associated or independent? For example, is customer satisfaction level dependent on the support agent's region? Under the section When to Use It, note that chi-square is only applicable for categorical data, not continuous values like height or weight. It's widely used for goodness of fit tests, where you check whether your observed distribution matches an expected one. Test of independence, where you check whether two categorical variables are related or not. Keep in mind, chi-square is a foundational tool in data-driven decision-making, particularly when your data isn't numerical in nature, but rather grouped or labeled. Before we run a chi-square test, we must ensure certain assumptions are met to make the results statistically valid and reliable. Let's walk through the 4 key assumptions. 1. Data are counts or frequencies. Chi-square works only with frequency data. That means we are counting occurrences of categories, like how many customers chose each product. not measuring things like weight or height. 2. Categories are mutually exclusive. Each observation should belong to only one category. For example, in a customer satisfaction survey, one response can't be both satisfied and dissatisfied at the same time. 3. Expected count per cell is generally 5 or more. This ensures that the chi-square approximation is valid. If any expected cell count is below 5, the test might not be reliable, and you may need to combine categories or use Fisher's exact test. Fourth, observations are independent. Each data point must come from a different subject or event and not influence another. So, if one customer gives multiple responses, that violates this assumption. Always check these assumptions before interpreting your test results, because if they're not met, your p-values might be misleading. This slide introduces the goodness of fit version of the chi-square test, which is used when we want to evaluate whether a set of observed frequencies matches our expectations. Let's break it down in 3 parts. 1. When to use. This test is appropriate when your y variable is numeric, specifically a count, and your x variable is categorical. For example, if you're measuring how many defects are reported across different product types, and you want to check whether these are evenly distributed or not. 2. Null and alternate hypotheses. The null hypothesis, H0, assumes that the observed data fits the expected distribution. In other words, the categories have no significant effect on the outcome. The alternate hypothesis, HA, proposes that the observed distribution is significantly different, suggesting that the X categories do influence the Y outcome. Example: let's say you're a quality manager tracking number of defects across different product types, A, B, and C. You want to know if the defects are uniformly distributed, or if a particular product is significantly worse. That's where the chi-square goodness of fit test helps you decide if the variation is random or meaningful. In summary, this test helps you validate if your data fits what you expect, and if it doesn't, it tells you which category might be the outlier. Now let's take a closer look at a special type of chi-square application, the one-proportion test, also known as the one-variable chi-square test. This test is used to determine whether the observed proportion of a specific outcome in a sample is significantly different from a known or expected value. For example, let's say we expect 80% of customer complaints to be resolved within 24 hours, and we want to test if our current performance actually matches that expectation. Under the When to Use It section, use this test when you have binary data. For example, pass, fail, yes, no, defect, no defect. It is specifically used to compare the proportion of a single outcome against a benchmark or known value. Make sure that the sample size is large enough for the test to be valid. The rule of thumb is ONP greater than or equal to 5 and N1 minus P greater than or equal to 5. This ensures a reliable approximation to the chi-square distribution. So, if you're working with a single categorical variable and want to validate if the occurrence rate matches expectations, this is your go-to hypothesis test. To properly conduct the chi-square goodness of fit test, we must first validate certain key assumptions. These are non-negotiable if we want to ensure the accuracy and integrity of our statistical conclusions. Let's walk through each of the 4 assumptions presented on this slide. 1. Random sample selection. The data must be randomly selected from the population. This reduces bias and ensures the sample represents the larger group. If the selection isn't random, we risk skewed results that don't generalize. 2. Independent observations. Each data point must be independent of the others. That means the outcome of one observation shouldn't influence the outcome of another. Violating this assumption could inflate or deflate your chi-square statistic. 3. Data follows a binomial. Distribution O, the chi-square test, assumes a binomial or multinomial distribution. In essence, we are looking at how many times something happens, like a success, versus how many times it doesn't, within defined categories. 4. Sample size large enough for normal approximation. O, for the chi-square test to work well, the sample size must be large enough. Specifically, the expected count in each category should generally be 5 or more. This helps approximate the normal distribution needed for accurate results. These assumptions are foundational. If any one of them is not met, the p-values we generate from the test might not be trustworthy. So before running a goodness of fit test, always check these 4 boxes first. Let's now interpret this visual. The goodness of fit chi-square test chart. This bar graph shows the observed versus expected values across different categories. In this example, individuals like Anish, Gaurav, Mohit, Nitin, Biki, and Pankaj. The orange bars represent the expected values, what we would anticipate if the distribution were equal or based on some hypothesized proportion. The blue bars represent the observed values, the actual data we collected. The key insight here is to compare the magnitude of difference between these bars. Look at Gaurav. The observed count is significantly higher than expected. On the other hand, Pankaj has a much lower observed count than expected. In a chi-square goodness of fit test, these differences are what we measure. If the differences between observed and expected values are large enough across the board, the chi-square test will likely give us a low p-value, indicating that the distribution is not what we expected, and x significantly impacts y. You don't need the actual numbers here. Just looking at the visual deviation between observed and expected gives you a quick feel for where the discrepancies lie. This is a powerful diagnostic for identifying whether any category is overperforming or underperforming compared to a baseline expectation. Now let's look at how we interpret the actual output of the chi-square goodness of fit test. Here, the system is evaluating if the number of observations across different team leaders, Anish, Gaurav, Mohit, Nitin, Biki, and Pankaj, follow a certain expected distribution. Let's break it down step by step. 1. Look at the p-value. You'll notice the p-value is 0.000, which is less than 0.05. This means we reject the null hypothesis, H, and accept the alternate hypothesis, H1. In simple terms, the distribution we observed is significantly different from what we expected. So X team leader significantly impacts Y number of PTP kept. 2. Look at the contribution to chi-square. Each row shows how much that team member contributes to the total chi-square value. For example, Pankaj contributes 241.189, which is massive compared to others. This means his actual performance is very different from what was expected, possibly indicating a special cause or area that needs deeper analysis. 3. Check the graph. As we saw in the previous slide, the bar graph clearly shows where the big differences lie between observed and expected values. Important. Note, by default, this test assumes that each category, team leader, should have an equal share. But if you know that categories should have different expected proportions, say based on historical data or headcount, this slide covers the chi-square test using a two-way table, which is a method used to evaluate the relationship between two categorical variables when both are recorded as counts. Let's go through the key elements. When to use. You apply this test when both the dependent variable, y, and the independent variable, x, are in numeric count form, but still categorical in nature. For instance, if you're comparing counts of defects observed across different numbers of full-time employees, FTEs, on a production line. Hypothesis statement. The null hypothesis, H0, says that there is no significant relationship between X and Y. The alternate hypothesis, H1, suggests that X significantly impacts Y, meaning there's an association between the two variables. Example. Let's say we're checking if the number of FTEs working on a production line has an effect on the number of defects produced. Each row of your two-way table would represent different levels of FTE count, and each column would represent the observed defect counts. This test is highly useful in operational analytics, where you're looking for relationships between categorical inputs and outputs in the form of frequency data. You'll often use this in process audits, root cause analysis, or team-based performance comparisons. Remember, while the data is numeric, it reflects counts in categories, not continuous measurements. So even though it may look like continuous data, the underlying structure is categorical. This slide covers the chi-square test using a two-way table, which is a method used to evaluate the relationship between two categorical variables when both are recorded as counts. Let's go through the key elements. When to use. You apply this test when both the dependent variable, y, and the independent variable, x, are in numeric count form, but still categorical in nature. For instance, if you're comparing counts of defects observed across different numbers of full-time employees, FTEs, on a production line. Hypothesis statement. The null hypothesis, H0, says that there is no significant relationship between X and Y. The alternate hypothesis, H1, suggests that X significantly impacts Y, meaning there's an association between the two variables. Example. Let's say we're checking if the number of FTEs working on a production line has an effect on the number of defects produced. Each row of your two-way table would represent different levels of FTE count, and each column would represent the observed defect counts. This test is highly useful in operational analytics, where you're looking for relationships between categorical inputs and outputs in the form of frequency data. You'll often use this in process audits, root cause analysis, or team-based performance comparisons. Remember, while the data is numeric, it reflects counts in categories, not continuous measurements. So even though it may look like continuous data, the underlying structure is categorical. This slide highlights the key assumptions we must meet before using a chi-square two-way table test, which is used to test the independence between two categorical variables. Let's walk through each assumption. One, data must be in the form of counts or frequencies. We are working with the actual number of occurrences in each category, not percentages or continuous values. For example, we're counting how many people chose each response option, not the average of something. Two categories must be mutually exclusive. Each observation should belong to one and only one category. There should be no overlap. If a person falls into two categories at once, the results will be invalid. 3, sample size should be large enough. More specifically, the expected count in each cell of the table should be 5 or more. This ensures the approximation to the chi-square distribution holds true. If expected counts are too small, the test loses accuracy. 4, observations must be independent. Each count should represent a unique observation. No repeated measures. If two values are related, like before and after data from the same individual, then independence is violated, and this test should not be used. Summary: these assumptions are foundational. If they're not met, your chi-square results might be misleading. It's essential to verify them before drawing conclusions from the analysis. This slide shows us how to interpret the results of a chi-square test using a two-way table. Let's focus on the results section at the bottom. The chi-square value here is 27.327. The degrees of freedom, df, is 49. Most importantly, the p-value is 0.995. How to study the result? We begin by evaluating the p-value. The rule of thumb is, if p is less than 0.05, we reject the null hypothesis, H, and conclude that x significantly impacts y. If p is greater than or equal to 0.05, we fail to reject H, meaning x does not significantly impact y. In our case, p equals 0.995, which is much higher than 0.05. This means we accept the null hypothesis, H0. So, there is no significant relationship between the two variables in question. Simplified interpretation. Think of it this way. We compared observed counts with expected counts, assuming no relationship exists. The p-value tells us whether the difference between them is meaningful or just due to chance. Since the p-value is very high, we're saying the data is consistent with the assumption of independence. Tip for practitioners. When you see a high p-value like this, don't jump to take action. There's no statistical evidence of a connection, so focus your energy elsewhere. This slide introduces us to the chi-square test for cross-tabulation, a powerful technique for analyzing the relationship between two categorical variables. When to use? You should use cross-tabulation when both the y and x variables are categorical. Typical examples include binary outcomes like pass, fail, yes, no, or high-low, being compared with another categorical variable such as shifts, locations, or departments. This test is also known as the test of independence, where we want to see if the variation in one category has any relationship with the variation in another. Null and alternate hypotheses. Null hypothesis. H0. There is no association between x and y, meaning changes in x do not affect y. Alternate hypothesis. Cha. There is an association, meaning x significantly impacts y. Example. Let's say we want to analyze if shift timing, evening or night, affects accuracy outcomes. Pass, fail. We would set up a contingency table comparing how many passes and fails occurred in each shift. If the p-value from the chi-square test is less than 0.05, we can say shift timing significantly impacts accuracy. Tip for practitioners. Always ensure your data is in frequency counts, not percentages. And don't forget the key assumptions. Independence of observations and expected frequencies per cell should generally be greater than or equal to 5. This slide introduces the concept of cross-tabulation, also known as a contingency table or crosstab. Definition. Cross-tabulation is a method used to summarize and analyze the relationship between two categorical variables. It works by organizing the data into a matrix format that displays the frequency of combinations of the categories of both variables. Imagine you're working with data about customer satisfaction and the region they're from. A crosstab will help you easily see patterns, for example, whether satisfaction is consistently higher in one region compared to others. Why use cross-tabulation? 1. Summarize large data sets. It converts raw categorical data into a matrix that's easier to interpret. Rather than going through hundreds of lines of data, the crosstab presents it in a single view. 2. Identify patterns or relationships. Helps detect associations or dependencies between variables. For example, we might find that product complaints are more frequent during night shifts than day shifts. 3. Input for statistical tests. Crosstab data is the foundation for running the chi-square test of independence, which helps us assess whether the observed relationships are statistically significant. Closing thought. So, when working with categorical variables, always think about how cross-tabulation can simplify your analysis and set the stage for deeper statistical testing like chi-square. Let me know if you'd like to walk through an actual example or demo in Minitab or Excel. This slide outlines the 4 key assumptions we must satisfy when applying the chi-square test for cross-tabulation. Let's walk through each of these. 1. Both variables are categorical. This test is strictly for categorical data, such as gender, region, shift, yes, no outcomes, etc. If either variable is numerical, this test is not appropriate. 2 data are counts or frequencies. We must be working with raw counts, not percentages or continuous values. For instance, 20 people said yes and 30 said no. Those are counts. If your data is in percentages, it must first be converted to frequencies before the test. 3 observations are independent. Each observation in the dataset should represent a unique, unrelated unit. If observations are dependent, such as repeated measurements from the same subject, the test results will be biased. Expected cell counts should be at least 5. This is a common rule of thumb in chi-square tests. Each cell in your cross-tabulation should ideally have an expected frequency of 5 or more. If you have many small expected frequencies, the validity of the chi-square test is compromised. In such cases, consider using Fisher's exact test instead. Wrap up. If these assumptions are met, the chi-square test will give you a reliable indication of whether the variables in your dataset are independent or associated. Would you like me to show how to check expected cell counts using Excel or a statistical tool next? This slide presents a practical example of a chi-square test using cross-tabulation, specifically testing the relationship between attrition and designation. Breakdown of the output. We're analyzing whether attrition is dependent on the employee's designation, assistant manager, executive, SME, etc. We're looking at observed counts of attrited and non-attrited employees across designations. The test produced a Pearson chi-square value of 1.271. Degrees of freedom, DF, equals 4, and most importantly, a p-value of 0.866. Here, p equals 0.866, which is much greater than 0.05. This means we fail to reject the null hypothesis, HO. In plain terms, this tells us there is no statistically significant relationship between employee designation and attrition in this dataset. Summary: HO, null hypothesis, designation does not impact attrition. HA, alternate, designation does impact attrition. Since p greater than 0.05, we stick with HO. So, in this case, designation doesn't play a statistically significant role in attrition. This slide summarizes the 3 main variants of the chi-square test that we use depending on the types of variables, numeric or categorical, for both y, output, and x, input. Let's walk through each of them. 1 variable test. Goodness of fit test. When to use: when y is numeric count data, e.g., number of defects, and x is categorical, like production shift. Hypotheses: OHO, x does not significantly impact y. OHA, the rate quotient count differs significantly from the expected standard. Example: you might use this test to see if the number of defects varies across different production shifts. 2-way table. When to use: when both y and x are numeric discrete data. Hypotheses: same logic as before. Testing if x has a significant impact on y. Example: use this to check whether the number of defects depends on the quantity produced, where both are numeric counts, discrete. 3 cross-tabulation, test of independence. When to use: when both x and y are categorical. Hypotheses: again, HO assumes no impact or association between the variables. Example: you may want to examine if the production line, line A, line B, etc., has any relationship with the quality outcome, pass, she fail. Final thought: This table helps quickly determine which chi-square test variant to use in a given situation. Make sure your data meets the assumptions before choosing the test. We'll now move to hands-on examples for better understanding.